Okay, welcome back everyone. So today we're going to prove this number theory result, which is going to be very quick, and we're going to do it two ways, but they're both pretty related. And this is going to be a tool for the finale video, which is going to talk about, I'll reveal it now, Gaussian integers and how they relate to sums of two squares. So this will be important in the final, within that video. Okay, well, let's see how to start off here. So let's read the problem. So show that -1 is a quadratic residue mod p, where p is an odd prime, if and only if p is congruent to 1 mod 4. Okay, well, that tells us that we have to split the problem into two parts. The first part is we prove it in the first direction, and the second part is where we prove it in the opposite direction. So if we prove it in the first direction, so that would be this direction, let's consider what that would tell us. So in this case, we need to prove that -1 is a quadratic residue, implies that, well, p is congruent to -1. P is congruent to 1 mod 4. Okay, well, why don't we use some tools that we've used in the past? Here. So the tools that we're going to use are going to be the fact that, well, g to the p minus 1 over 2 is congruent to -1 mod p. Okay, and actually a fact that I liked earlier, or a fact that I kind of overlooked earlier in explaining why it has to be -1 and not 1 in the previous video, actually. My explanation was okay, but I think a nicer explanation is that if it was 1, so if it was 1, that would contradict the order of g being p minus 1. So yeah, I kind of like that explanation better. So therefore it has to be -1. And also, well, by definition, since -1 is a quadratic residue, we note that g to some 2k, just some even power, is congruent to -1 mod p. Okay, so now let's set these two equal to each other. So we have g to the p minus 1 over 2 is congruent to g to the 2k mod p. And it pretty much follows that these two powers must be, must have the same parity. So that therefore this one would have to be even, which would imply that p is congruent to 1 mod 4. But to be a bit more, even more rigorous, let's just use Euler's theorem and set the powers equal to one another congruent to one another mod p minus 1. So that tells us that p minus 1 has to be congruent to 2k mod p minus 1. Okay, and that tells us that p minus 1, which is going to be equal to p minus 1 times some q plus 2k. But that tells us that since this side is even, since p is an odd prime from the problem statement, this side is even. It's an even plus an even, which makes it even. So therefore we need this side to be even. But that happens exactly when p is congruent to 1 mod 4. Okay, so that finishes the first side. Okay? So now let's analyze the second side. I'll delete this. Computer age. Okay. Second case. So second, not really, it's not a case. It's second part. The other way. So we have to prove it the other way. So that implies that we need to prove that if p minus 1, p is congruent to 1 mod 4, that implies that -1 is a quadratic residue. Let's see. Well, we're going to use the same tools here, but really all we have to use is this tool. And then, well, we'll see what happens in a second. So if p is congruent to 1 mod 4, we can plug that in here. If it's congruent to 1 mod 4, then that tells us that this power is going to be even, because that tells us that p is 4 times some k plus 1, and therefore our power is going to be g to the 2k. It's congruent, and then we're going to be left with it's congruent to -1 mod p. But as you can see, if we have g to the 2k is congruent to -1 mod p, that tells us that -1 is a quadratic residue. So that actually finishes our proof. So that is the first way. And the way that I talked about earlier regarding the Euler's theorem, not Euler's theorem, Euler's criterion, it's heavily related to this, but I'll show it to you. So I think it's much nicer. It's much faster in my opinion. But to do that, you would most likely have to prove Euler's criterion, which we have, so we're safe in doing and using it. But let's see. So we're going to have that if we plug -1 into here, into Euler's criterion, we're getting it the Legendre of -1 is congruent to -1 to the p minus 1 over 2 mod p. So this is given, or this we know. We're not making any assumptions right now. But now, let's prove it the first way. So if -1 is a quadratic residue, this will evaluate to 1. So 1 is congruent to -1 to the p minus 1 over 2. But for this to be the case, -1 would be have to raise to an even power. Therefore, this has to be even, and by similar reasoning to last time, p has to be congruent to 1 mod 4. So that finishes the first way. So the second way, well, we have to prove that if p is congruent to 1 mod 4, then -1 is a quadratic residue. Well, think about it. If we plug in 1 mod 4 in here, we're going to get an even power raised to -1, or -1 raised to an even power. So we're going to get 1 on this side. So 1 is congruent to the Legendre of -1 mod p. But notice that that just tells us that, well, the Legendre of -1 is 1, so therefore that tells us by definition that -1 is a quadratic residue. So that actually finishes the proof in a different way, slightly different way. So I hope you enjoy that proof, and again, it's a pretty short video because this proof is merely a tool rather than a singular video on its own. But yeah, again, we'll use it in the finale. So I hope you enjoyed this video, and have a nice day. Goodbye. Very nice.